Hello students, welcome to my channel. Uh, Hope all are fine. So today, actually, before I go to discuss about division algorithm, last video I assured you to do the sum number 11 of exercise 3.1 again because there was some confusion in number 11. So let me explain today again number 11 of exercise 3.1. Exercise 3.1 number 11. I want to explain again because there was some confusion in the last video. I hope you all remember. So there was given actually factorial n. Factorial n is greater than 2 to the power n. 2 to the power n. And there is also condition given n is natural number and n is greater than 4. These conditions were given. So as we know, everything we have to do by same process as one means by putting the value of n 1 to whatever it is, then sk plus 1. We have to go for three conditions that we already knew. You already got everything. So process will be same. So let us apply first. Let s n equals to factorial n greater than 2 to the power n. Now, as all the sums were done by same process, here also we will do same process, but we know that n is given there greater than 4. So we will try for 1, 2, 3 like that. We will try for till 4, but that will not be true, we know that, but still we will do for n equals to 1. N equals to 1, LHS is equal to factorial 1, equals to 1 only, and right hand side 2 to the power 1, that is 2. So here it is seen that LHS is not greater than RHS. So Sn is not true for n equals to 1. So like this, if we go for 2, 3, 4, because we can do orderly now, 2 will be factorial 2, 2 to the power 2, 2 to the power 2 will be 4, this side bigger, factorial 2 is 2 into 1, 2 only, so 2 will be smaller, not greater than 4, no? So like this, 3, 4, suppose 4, factorial 4, let us do for 4, for n equals to 4, let us do, L is S is equal to factorial 4. Let us do the calculation. 4 into 3 into 2 into 1. 4 is a 12, 12 is a 24. Then RHS is 2 to the power 4 because n is equals to 4 taken. So 2 to the power 4 is 16. 2 to the power 4 is 16. Actually, the question was little wrong. It should be n is greater than equal to 4. Then now we have got n equals, if n equals to 4, then LHS, then LHS is greater than RHS. That means Sn is true for n equals to 4. Then 5, of course, 6, because n is greater than equal to 4. N is equal to 4 and greater than 4. It is actually something wrong here. It should be n is greater than equal to 4. The question is little wrong. So it should be greater than equal to 4. If you go for 5, then also it is correct. 2 to the power 4, 16, if it is 5, let us do orally. 5. So factorial 5 will be 4, 3, 2, 1, means 5, 4, 3, 2, 1. 24 into 5 is 120. 2 to the power 5 is 32. So 120 is greater than 32. So 5 will be okay. 6 will be okay. 6 will be true. 5 will be true. 7 will be true. So from 4 onwards, 4, 5, 6, 7, any numbers if you do, then for Sn will be true. Sn will be true. Sn is true for n equals to 4. Now, where we will go? We will go to Sk. Let us assume, same process is same. Let us assume Sk factorial k greater than 2 to the power k be true for n equals to k. That is same thing. Now to prove that, what is to prove? To prove that k plus 1, prove that as k plus 1 such that factorial k plus 1 is greater than 2k to the power plus 1 is true. That is what we have to prove. Now, since there is in between no equal sign, there is greater than, means inequalities. Already you got inequalities. So we will not do what is called left hand side, right hand side actually. It is not needed to do because we are going to prove left hand side is greater than right hand side. So we will take the help of this. Since, because we know already we have assumed that as k factorial k is greater than 2 to the power k. Factorial k is greater than 2 to the power k. Factorial k is greater than 2 to the power k. This one is just take as number 1. Next will be, we can think, I will explain you, k plus 1 is also greater than 2. Now look here, what is n? N is, suppose n is equal to 4, suppose, because the equal sign is also there, n is greater than 4, 5, 6, 7, anything, but let us take n equals to 4. So here n equals to 4 we have taken. Now in place of n, what we have taken? K. That means k equals to 4. Now in place of n we have taken k plus 1. In place of n we have taken k plus 1. So k plus 1 is greater than equal to 4. N means k. So k is greater than equal to 4. If in place of n we are putting k plus 1. K plus 1. So k plus 1 is greater than equal to 4. So k plus 1 is greater than 4. Equal limit. Greater than 4, or you can write equal also, no problem. Because if it is equal, no problem. If it is not only greater than, then also no problem. Process is same. If it is only greater than or greater than equal, process is same. What we have understood, k plus 1 is equal to 4 or greater than equal to 4. K plus 1 is equal to 4 and k plus 1 is greater than 4. Now, I have written here k plus 1 is greater than 2. Look here, k plus 1 is greater than 4. K plus 1 is greater than 2 plus 2. Or we can write k plus 1 is greater than 2. If k plus 1 is greater than 2 plus 2, then k plus 1 will be greater than 2 also. Like 10 is greater than 4 plus 2. 10 is greater than 4 plus 2. 4 plus 2 is 6. So we can write also 10 is greater than 4. I hope you understand this. 10 means k plus 1. Assume k plus 1 is 10. Is equal to 2 plus 2, 4 plus 2. But here in place of 4, we could have written 3 plus 1 also. But we will not use 3 plus 1 because there is, what is to prove? 2 to the power k plus 1, not 3 to the power k plus 1. So we will take 2. 2 plus 2, any 2 we can take here. So that is why I have written here k plus 1 is greater than 2. This is equation number 2. This one all of you have understood. I means whatever I have explained here, I hope all of you have understood. Once again let me explain. 10 is greater than 4 plus 2, so 10 is greater than 4. Or 10 is greater than 2 plus 2. Then 10 is greater than 2, same thing. 10 means k plus 1. K plus 1 is greater than 4. Why k plus 1 is greater than 4? Because condition is given. N is greater than 4. N is equal to 4, but greater than 4. So if it is n is k plus 1 is greater than 4, k plus 1 is greater than, k plus 1 may be 5, 6, whatever it is. But k plus 1 is greater than 4. We could have written 3 plus 1, but we will not use 3 plus 1 because in right hand side 2 is there, no 3. So we have written 2 plus 2. So k plus 1 is greater than 2. This is the condition. Now 1 into 2. 1 and 2 will multiply. Left hand side into left hand side we will multiply. K into factorial k into k plus 1 greater than right hand side multiplication 2 to the power k into 2. Now this can be written this way also, k plus 1 factorial k, same meaning. Here 2 to the power k into 2 to the power 1. This one nothing is done, just place is changed. So k plus 1 factorial k will be k plus 1, this one already I explained how it is. 6 into factorial 5 equal to factorial 6. This one you have understood, I think. This previous video I already explained. 6 into factorial 5 will be factorial 6. It means greater number into small factorial. Greater number into factorial of smaller number equals to factorial of greater number. This is greater, k plus 1 is greater, like 6. Or this one we can write this way also, 5 plus 1 into factorial 5. So factorial 5 plus 1. So this one you understood, I know. So 2 to the power k into 2 to the power 1. Power can be added. So other things we can write as all the sums done. So this is clear to all, I hope. Still, if any problem in number 11, so please inbox me, write a comment in the inbox so I can explain again. Now we will go to division algorithm. Division algorithm means this is related to division. So any number we divide by any other number, then we get a quotient. We also get a remainder. Sometimes remainder may be 0 and sometimes remainder may be greater than 0. So that is division algorithm. So the conditions, we are going to learn the conditions related to division. Division algorithm. The students have already acquired the concept of division along with addition, subtraction and multiplication in arithmetic. Because in arithmetic, in general maths, already we have got relation among addition, subtraction and multiplication. Here we shall discuss about some important properties and application associated with the operation of division in integers. Remember that what is there? Integers. We are going to do everything with integers. Integers means Z. Z. The symbol of integer is Z. The division in integers. The operation of division of an integer by another integer is known as division algorithm. The operation of division. Operation of division. Division by an integer. Division of integer by an integer. One integer will be divided by another integer. That is called division algorithm. Division algorithm. This is very, very important. When you go for a higher studies for computer, in computer also in higher classes I am saying, not in class 10 and 9 like that. In future, if you go to learn something about computer in higher classes, then this will be required. The algorithm, division algorithm, many more algorithms are there. So this algorithm will be required. So algorithm. So what we have understood now, one integer will be divided by another integer. The process is called division algorithm. Whatever process we do. So theorem number 1, that is division algorithm. For two integers a and b with b greater than 0, there exist unique integers q and r such that a equals to bq plus r. So what we are going to get in theorem number 1, a equals to BQ plus R. What is A, what is B, what is Q, and what is R? We are going to know. Here condition is there that 0. This is theorem number 1. R is greater than equal to 0 and smaller than B. R is greater than equal to 0 and smaller than B always. So when we divide a number, suppose 19, we are going to divide by 3. 3, 6, 18. Remainder is 1. So here this one you can write like this also. 19 is equal to 3 into 6 plus 1. 19 is equal to 3 into 6 plus 1. We can write like this, because 3 into 6 is 18. 18 plus 1 is 19. So 3 into 6 plus 1 is 19. So dividend is equal to divisor into quotient plus remainder. This one already you got in general maths. Dividend, this one dividend, this one divisor, this one quotient, this one remainder. Dividend is equal to divisor into quotient plus remainder. This one you got in your general maths part. So here think that this 19 is A. 19 is A. We are dividing by a divisor B. How many times? Q, quotient. Remainder is R. See, this B and A taken different letters, but quotient is Q, remainder is R. This one you can remember. This is B, this is Q, this is A, and this is R. So by B, if you divide A, you will get a quotient Q and you will get a remainder R. I hope you understand. B is equal to, A is equal to BQ plus R. A is equal to BQ plus R. A is equal to B into Q plus R. A is dividend 19. 3 is divisor or divisor, you can say anything, 3. And 6 is quotient plus 1 R. And this R, what is R now? Remember, do you know the fact about R? What is remainder? Remainder will be always smaller than B. That means divisor. Look here. Suppose by 5 you are dividing 36. Then if we do 5, 6 are 30, remainder is 6, which is wrong. Why it is wrong? Why it is wrong? Because remainder is greater than divisor. Cannot be. It cannot be. This is R, this is B. B. This B and R, there is relation. So how do we come to know that a division is correct? By looking the remainder, we understand that division is correct or not. Here, by looking remainder, by getting remainder, we understand that the division is correct or not. Here, remainder is greater than 5. Divisor. Remainder is 6 and divisor is 5. This cannot be happen because this is only wrong, that you know already, because it should be 5, 7, 35. 5, 7, 35. Then 1 will be remainder. 1 is smaller than 5. Then only it is correct. That is why R is always smaller than B. Remember that. R means remainder. Remainder must be always smaller than divisor. This is divisor. This is example. You can take any example. You can take any example. by looking the remainder we understand that the division is correct or not. If remainder is greater, division is wrong. If remainder is smaller than divisor, then the division is correct. And the r may be equal to 0 or may be greater than 0. Here sometimes we get, suppose 5, here it is 35. If we divide by 5, 7 by 35, so 0. We may get a remainder 0. Or you may get remainder greater than 0, any number. Here generally we don't get negative number. In this type of simple division, we don't get negative number. So remainder may be 0 or greater than 0. So remainder starts from 0. Here 0, 1, 2, like this. But whatever we get, that must be smaller than b. What is b? B is a divisor by which we divide a number. That is called divisor. That is called divisor. You can pause the video and you can note it down, no problem for you. So let me write this way. Dividend will be inside. This is divisor, and this is quotient, and here remainder. Always remainder may be 0. Remainder, because when the number is divisible, then we get remainder 0. 15 is divisible by 5. That means remainder is 0. 16 is not divisible by 5 because remainder is 1. 16 if we divide by 5, 5 3s are 15, remainder will be 1. Whatever it is, we will get remainder always 0 onwards. But only to remember that this condition, r must be always smaller than b. What is q? Q is always integer, any integer. Q is always any integer. Anything. 0 to minus 0 to plus, any integers. So I hope this one you have understood. So next, proof of this division algorithm, that is theorem number 1. Theorem number 1 actually we are going to prove now. What we have got in previous one, A equals to BQ plus R. We have got actually A equals to BQ plus R. And what is R? This one you have to remember always. You have to remember. There is written we have A, B belong to Z and B is greater than 0. Therefore, for any x belongs to Z, A minus xB belongs to Z. A minus, this one, look here. A minus BQ is equal to R. If BQ goes this side, minus BQ equals to R, remainder. This is remainder. Here what is to prove? A minus BQ, whatever we get, that should be an integer. A minus BQ. Here in place of Q there is written X. A minus XB or BX, same thing. XB or BX. A minus BQ or QB, same thing. So here in place of Q put X, because in this theorem which belongs to Z, that is what we have to prove here. Theorem number 1. Theorem number 1, this one. So whatever given, what is given? A minus XB. This A minus XB we just take as let, it's a set. What is the set? A minus XB such that A minus XB is greater than equal to 0. And what is X? Belongs to X is an integer. A minus XB is greater than equal to 0. A minus XB, A, B belongs to Z and B greater than 0. So what we have taken? We have taken let. S is a set. A minus XB is greater than equal. We have taken let, this one, let. Here we are going to get a positive integer. positive integer because greater than equal to 0. Either 0 x minus a minus xb, we will get either 0 or greater than 0. 1, 2, 3, 4, whatever it is. And what is x? X will be an integer. Look here, if a minus, here if we get a smaller number, from a if we subtract, we will get a positive number. If a is bigger and xb, whatever calculation, if it is smaller, from greater number, if we subtract smaller number, then we will get a positive number. Again, x is z, z means integer, maybe positive, maybe negative. Suppose in place of x, negative number, minus 3 suppose, in place of x minus 3, then what will be the calculation? Minus minus plus, so then also you will get a positive integer. In place of x, if you put a positive number, you will get greater than equal to 0, maybe 0 or more than 0. If you put in place of x negative number, then also you will get a positive number, means greater than 0 or maybe equal to 0. That is what we have taken let, this is considered. We have considered that a minus xb is greater than equal to 0. Now, here there is given a, b both belong to z. This is given in the question. This is given here. So, since b belongs to z, this one is done, just I will explain, I will make you understand what is done actually here. A, b belongs to z and there is also given b is greater than 0. Look here, b is an integer, but there is one more condition given, b is greater than 0. That means what? Positive. Greater than 0 means no negative. Positive integer. 1, 2, 3, 4, anything. Because of this condition given in the question, given in the theorem, that is why we have come to know that b is a positive integer. Now, so if b is greater than 0, then what can be written? B is equal to 1 or b is greater than 1. Can you write this? B is greater than 0. So b is equal to 1 or b is greater than 1. This one shortly, how can you write? This one we can write shortly. Instead of writing separately, we can write one separately, together like this. B is equal to 1, b is greater than 1. This condition from where we have got? From this condition we have got. B is in integer, b is greater than 0. So b will be starting from 1. That is why b is equal to 1 and b is also greater than 1. That means 1 onwards. So b is greater than equal to 1. That is why this is written like this. Whatever is written here, I want to explain you what is written there. Then therefore, what is done here? Modulus of a is multiplying here. This one. Okay. Let me do here only. This one, let me write again. B is greater than equal to 1. Both sides multiplying by modulus of a. Mod of a means a is positive and negative. Modulus of a is always positive. If you put in place of a, suppose 5, modulus of 5 is 5. If it is minus 5, then also 5. Both will be positive. Modulus of plus 5 is 5. Modulus of minus 5 is also 5. So that is why here, therefore, modulus of both on multiplying by mod a both sides. So now we will assume this one here equal sign is also there. So we are taking x equals to what we have taken? Modulus a. Now we will take x equals to minus modulus of a. Putting x equals to minus mod a in a minus xb in the set here. In a minus xb. We will put now. So a minus xb is equal to a minus x is minus modulus a. Minus modulus a b. Just putting the value of x minus mod a. X equals to a minus xb, a minus mod a b. I hope you understand this one. Equals to a minus plus mod a b. A plus mod a b. Now Now this one is greater than equal to A plus mod A. Why? This one, why you can? A is A, mod A is A, B is neglected. Why B is neglected? Since mod of A, B is greater than mod A. Where you have got? Look here. This one, mod of this one. Mod of A into B is greater than A. Equal is okay there. So here there is written condition. Condition is written mod of A, B is greater than mod of A. Mod of A, B. This one greater than mod A. Greater than mod A. Greater sign is there. Greater sign is there. Now this one and this one. This one if you are already done. This one already I explained it. Okay. Now is greater than equal to 0. Why it is 0? Why it is 0? Mod A plus A is greater than 0. Now look here. Mod of 5 plus 5. Mod of 5 plus 5 is greater than either 0 or greater than 0. This one will be either 0 or greater than 0. Greater than 0. If it is mod 5, this is plus 5. 5 plus mod 5 is always either 0 or greater than 0. You will never get here negative number. Either 0 or greater than 0. You will never get a negative number. That is the meaning here. So for x equals to mod minus A, we have got A minus xb is greater than equal to 0. So A minus xb belongs to the set. This one, this set. A minus xb belongs to set. What we have got? A minus xb is greater than equal to 0. That means this is positive. A minus xb, whatever you get, that will be positive because greater than equal to 0. It will never be negative. And A minus xb is equal to something we have got. That means s equals to this one is not null set. Not null set. Or non-empty set. Non-empty set and positive. Non-negative, positive, same thing. In other words, S is non-empty set of non-negative integer. So A minus xb, always we will get something, and in some number you will get, and always we will get a positive integer. Positive because greater than equal to 0. This is theorem number 1. Theorem number 2. Theorem number 2, there is written whatever already we have done, that is what here given. A equals to BQ plus R where 0 R B. This is mod B. This is theorem number 2. A equals to BQ plus R, this one already we have got. This one only difference is what here mod B means plus B minus B both are they are inside mod. That is what we have to show here. Theorem number 2, we don't have to prove like that. Just we will do directly by taking some example. This is in page number 108. Page number 108. Page number 108. Some examples are given by taking A equals some number, B equals some number, Q, like this some numbers are taken. So after it is shown. Illustration. A equals to 20, B equals to minus 3. A equals to 20. A equals to 20, B equals to minus 3. Because B we can take plus 3, minus 3 both. Because there is written mod B. A is 20, B equals to 3, minus 3. So what is B? A is 20. That means while divide, 20 will be inside. B is 3. Divisor. Sorry, minus 3. B is minus 3, no? Yes, B is minus 3. Now we have to divide 20 by minus 3. So what we will write here? Then only we can write like this, no? If we don't put minus sign here, minus will come. That will be difficult. Because that if we get minus here, suppose here plus, then here if we subtract, then it will become 38. I will explain again. You may not understand. What is A? 20. I have written 20 here. What is B? Minus 3. Now by minus 3 we have to divide 20. 3, 6, 18. But minus 3 into 6 is minus 18. So this one we have to subtract. Always we know while division here these two numbers we have to subtract. While subtracting here minus sign is there, so it becomes plus. So this 20 plus 18 it becomes 38. This 38 is greater than minus 3, which is impossible. 38 means remainder. Remainder cannot be greater than B. Condition is given here. So minus 3 into minus 6 we have to do. Then only we will get here remainder small. I hope you got my point. Minus 3 into minus 6 is plus 18. Now we can subtract 2. Okay. So Q is equal to minus 6. R is equal to 2. Now we have to prove this one. A is equal to BQ plus R. A is 20. B is minus 3 into Q. Q is minus 6 plus R. R is 2. So this one minus 3 into minus 6 is 18 plus 2, 20. So both sides equal. Both sides equal. So what we have got here? What we have got here? This condition. Let us write this condition. 0 R. Here we will write minus 3. In place of B we have got minus 3. So mode is there. So this way, what we have got R? R is 2 greater than 0. R is smaller than B. What is R? R is 2. That is smaller than 3. Mode of minus 3 is 3 only. So because this is 2, what is called? A remainder is 2, and which is smaller than 3. Mode of minus 3 is 3, mode of plus 3. So you can, this one you can verify by taking any number. A is 25, B is 6, any number you can take. B is minus 6, B is minus 10, 10, any number you can take and you can verify. Whatever is done here, you can do by yourself for theorem number 2. (3.3.1) idea of even and odd integer. So let me say one thing again. Always remember what we have remembered: BQ plus A equals to BQ plus R. This one, and Q is always integer. Always Q. This one is very important part. Q. Whatever the value of Q, that will be always integer. You have to show Q is integer. You have to show Q is integer. Multiplication Q into anything. Q into anything. Q plus anything. So Q into anything, Q plus anything will be always integer. I hope you understand this one. Because Q is itself an integer. Q is integer. Suppose minus 5. Suppose minus 5. Minus 5 into 3. Anything. Minus 5 into P. Minus 5 into 9. You will get an integer number. Always. So remember that Q is very important part for you. Here what we have to prove, we have to show idea, we have to understand that even integer and odd integer. So A equals to BQ plus R. R is greater than equal to 0 and R is smaller than B. So this is the condition here taken. Let us take B equals to 2. Why B equals to 2 taken? Because we are going to get even and odd. Even, let us see even first. A equals to BQ plus R. Now what we will take? B equals to 2. B equals to 2. Then what we get? A is equal to B is 2. 2Q plus R. 2Q plus R. So here this condition is given. What condition was given? Let me write here only. Then you will understand. This one we will write again now. Comma 0. This sign R. B. B is 2. So R is greater than or equal to 0 and R is smaller than 2. Whatever we have written, that just as it is we have to write only. There is nothing else. Then, so what is R now? This one is very important part. What is R? 0, 1. R is greater than or equal to 0. Equal to 0. So 0 I have written. R is greater than 0. So 1 I have written. But I cannot write 2 because R is smaller than 2. Got my point? I cannot write here 2, 3, 4 like that. The value of R will be 0, 1, only 2. Let me repeat. R is greater than or equal to 0. Equal to 0, so I have written 0. Greater than 0, so I have written 1. But I am not going to write 2 because R is smaller than 2. That is why R means 0 and 1. Now, if R is equal to 0, then A is equal to 2Q plus R is 0. So what we have got? A is equal to 2Q. A is equal to somewhere got A is equal to 2Q. What is Q? Q is always an integer. Remember. So by putting the value of R 0, we have got this one. Now next R is equals to 1 also. No? So if R is equal to 1, then A is equal to 2Q plus 1. A is equal to BQ plus R. A, B. B is 2. B is 2 already. We have got now here. A equals to 2Q plus R. A is A, 2Q is 2Q, R is equal to 1. In place of R, 1 is written. Okay. Now, A is equal to 2Q plus 1. Here, okay, 2Q plus 1. Here also Q is an integer. A is equal to Q plus 1. Q is also an integer. So now we will come back here. Q is integer. 2 into any integer. 2 into any integer will be always even. Do you understand? 2 into anything is always even. So what is Q? In place of Q we can write 0, plus minus 1, plus minus 2, plus minus 3 and go on. Now, Q is integer, any integer. So 0, plus, minus, integer. Positive, negative, both we have to take. But whatever in place of Q, A equals to 2Q. What is A? A is, while division, this is A. Dividend. So A is equal to BQ plus R. A will be always even when we get A equals to 2Q. 2 into Q, 4 into Q, but we have to show here even. This one. Here also Q is equal to 0, plus minus 1, plus minus 2, etc. 2Q plus 1. 2 into 0, 0 plus 2 into 0, 0 plus 1 is 1. 2 into 2, 4. 4 plus 1 is 5. 2 into 3, 2 3 is 6 plus 1, 7. So anything you multiply with Q, any integer if you multiply with Q, you will get always odd number. So for even what we have got, A is equal to 2Q, Q is integer. For odd what we have got, A is equal to 2Q plus 1. Whatever you put in place of q, the result of a, the calculation for a will be always odd. Suppose 2 into minus 3. 2 3 is 6 plus 1 7. 7 is odd. Let us put minus 3 also. Plus 1. 2 into minus 3 is minus 6 plus 1, that is minus 5 is odd. Minus 5 is also odd. So in place of q, any number, positive or negative, doesn't matter. So you will get always an odd number. So what we have to remember, 2q and 2q plus 1. What is q? Q is any integer. So for even, this is the formula. For odd, this is the formula. Example 1. Show that the square of any integer, square of any integer is expressible in the form of, it can be expressed in the form of 4m or 4m plus 1. 4m plus 1. Previous one, 2q or 2q plus 1. Even and odd. Here 2q, 2q plus 1. 2m, 2m plus 1. 4m, 4m plus 1. So meaning is same. So what is actually we have got a equals to bq plus r. This one always remember that. Remember this always. Okay. Now what we have to take? Yes. Let us consider an integer a and b. I am writing shortly because it is done already. A and b, we will take a is a only and b we are going to take 2. Why 2? Why 2? Because 2 is related to 4. In the previous sum, 2q, 2q. So if we get 2q, then for us it will be easy. We will make it 4m only, but we will understand while doing the sum. So if b is equal to 2, then this one can be written this way. 0 r in place of b 2. In place of b 2. What does it mean? R is equal to 0, 1. R is greater than equal to 0 and R is smaller than 2. So R is equal to 0, 1. Hope all of you understood. So we will put the value now. For r is equal to 0, we will do the calculation. For r equal to 1 also, we will do the calculation. For r equals to 0. R equals to 0. A is equal to 2q plus r. This one I forgot to write. A is equal to, A is A, B is 2. B is 2 because we have taken let B equals to 2. So in place of B, 2 written, Q as it is, R as it is. Now in place of R, first we will put 0, next we will put 1. A is equal to 2Q plus R, 2Q plus R, or A is equal to 2Q plus 0, R is equal to 0, or A is equal to 2Q. Here this is not finished. Square of any integer, square. So we have to do both sides square. So A square is equal to, directly I can write 4Q square. 4Q square. Here again we can write A square is equal to 4. What is Q? Q is always integer. I have told you already. Q is always integer. So Q square also integer. 4 into Q square also integer. Or 4m. What we have done, in place of Q square, m written. Why? Because in the question 4m given. So in place of Q square, we have written 4m and we have to write this sentence where m is equal to Q square and this Q square is always belongs to Z. What is m? Q square. What is Q square? Q square is an integer. Q is an integer, so Q square also integer. So A square equals to 4m, we have proved. Square of an integer is expressible in the form of 4m. So we have expressed in 4m. Now we have to express in 4m plus 1. Okay, let us see. Now for r equals to 0 we have done. Now for r equals to 1, r equals to 0 comma 1, we will do r equals to 1 now. Implies a equals to 2q plus r. A is equal to 2q plus 1 because r equals to 1. Now we have to do squaring. Here squaring we have done. Here also we have to do squaring because square is written. So squaring both sides, 2q plus 1, because all of you know that squaring cannot be done in one side. So squaring must be done both sides. That all of you know. So a square is a plus b whole square. A square plus 2ab plus b square. A square 4q square plus 4q plus 1. A square is equal to 4. In bracket, we will take common from these two terms. Q square plus q plus 1. Now we will write a square 4. In place of q square plus q, we will write m plus 1 plus 1. 4m plus 1. In the question 4m plus 1 you have to use. So this is very easy. There is nothing to do. Q square plus q, where m is equal to q square plus q. In place of q square plus q, written m. So where m equals to q square plus q belongs to z, because q is z. Q is an integer, so q square plus q also integer. I hope you understand. This is what we have done. So that is why what we have understood now, that for any integer a square is the form 4m or 4m plus 1. So we have expressed a and a square in the form, a square in the form of 4m, a square in the form of 4m plus 1. We have expressed a square as 4m. We have expressed a square as 4m plus 1 as the question given. Example 1. Example 2. Show that the square of an odd integer can be written as square of an odd integer can be written as 8m plus 1. Square of any odd integer can be expressed as 8m plus 1. Here m belongs to z. M must be a integer. Whatever in place of m we write, like previous sum now, whatever we have written in place of m. In place of m we have written q square. So m belongs to z. Why m belongs to z? Because q square is an integer. Here also whatever in place of m we have written, that must be an integer. Why m is here also integer? Because q square plus q is also integer. Here in place of m, whatever we write, but m must be shown as an integer. Okay. Now, like previous sum, we will take let a and b be integers. Okay. Integers. Here a will be a only, and assume b is equal to 4. Why 4 taken? In previous sum 4 was there, 4 is taken. 8m is there, so 4 will be easy for us for doing any calculation. So that is why whenever you get 8, so we will take 4 only. So in the question in example number 3, I think. I hope 4 is taken. Example number 2. Yes, 4 is taken. So 4 is related to 8. 4 to the 8, it is divisible. So 4 is taken. Now rest all are same now. Since b equals to 4, we will write a is equal to, let us write first a is equal to bq plus r. 0 r, this is the formula. This one is main line. This one is the standard form. This is unstandard form. So in this only we have to do all the sums. So here we have taken b equals to 4. B equals to 4. So what you learn? A equals to 4q plus r. What is r now? B is 4. B equals to 4. So in place of B, 4 written. So what is R now? R is equal to 0, 1, 2, 3. R is greater than equal to 0. So 0 must write. R is greater than 0. So 1, 2, 3. 4 we will not write because R is smaller than 4. So like previous sum, R equals to 0, we will do the sum. R equals to 1, 2, 3. We have to do 4 times. 1, 2, 3, 4. So for R is equal to 0, we will write A equals to 4Q plus 0. R is 0. So A is equal to 4Q. We have written A equals to 4Q. Square of an odd integer. So we will do squaring. A square equals to 4Q whole square. Now A square is equal to 16Q square. We can write A square is equal to 8 into 2Q square. Same thing. 16Q square, we can write 8 into 2Q square. We will not add 4 for the 16Q square. Why? 4 for the we will not do, because here question 8m plus 1. 8m plus 1. 8m plus 1, no? Okay. Here there is one condition given, square of an odd integer. Okay, wait. Since it is given odd integer, so we will take R is equal to 1 and 3 only. 0 and 2 we will not take odd equal, no. So R equals to, we will take 1 and 3. So A equals to 4Q plus 1 and 4Q plus 3. A is equal to 4Q plus 1 and another one A is equal to 4Q plus 3. I hope you understand 0 and 2 neglected. Why? Because it is given odd integer. In place of odd, if it is given even integer, then we could have neglected 1 and 3 and we could have written here 0, 2. So once we will put R equals to 1, next we will put R equals to 3. A equals to 4Q plus 1 and A equals to 4Q plus 3. Now we will do squaring. Both we will do squaring. Let us do here. A is equal to 4Q plus 1. We will do squaring both sides. Why do we do squaring both sides? Because here written square. That is why we are doing square. If it is written cube, then we will do cubing both sides. So A square is equal, this one I will do directly. 4Q A square plus B square plus twice AB. A square 16Q square 2AB 18Q plus 1 square is 1 square is 1 only. 1 square is 1. So A plus B whole square, just formula is applied. Now look here. A square is equal to, from these two we can take 2 common. We can take 2 4 is 8, 18 little. 2 into 4, 8Q. 8Q plus 1. So from these two terms, we can take 2 common, we can take 4 common, we can take also 8 common. 16 and 8, they are divisible by 2, 4 and 8. But we will take 8 common. Why we will take 8 common? Because 8m there is 8. So let us take 8 common. 2Q square plus Q plus 1. Very easy. We have to make it whatever given in the question, whatever. But whatever we take, there should be Q, because Q integer. 8 in place of 2Q plus 2Q square plus Q, I have written here M plus 1. Only to write this one, there is nothing. There is nothing to learn here. M is equal to, where M is equal to 2Q square plus Q, which belongs to Z. This must, because Q is integer. Whatever you do squaring, you multiply, I have already told you. Add, multiplication, squaring, whatever you do, that result will be always integer. So 8m plus 1 we have got. But while putting r equals to 1 only we have got 8m plus 1. By putting r equals to 3 also we have to get 8m plus 1. Do you understand what I am saying? R equals to 1 and 3. By putting in A equals to 4q plus r, in place of r if we put 1 we get this. In place of r if we put 3 we get this. This one is squaring done, but this one is not done. This one we will do now. Again A is equal to 4q plus 3. Here also we will do squaring. A square is equal to 4q plus 3 whole square. A square is equal to 4a square plus 2ab plus b square. Again a square is equal to 16q square plus 2 4 8, that is 24q plus 9. Now a square is equal to 16q square plus 24q plus 8 plus 1. Why it is done? I will make you understand. A square is equal to, from these 3 we can take 8 common. We have to take 8 common because there is 8m. After taking 8 common, here it is left 2q square, 3q plus 1. 8 1 is 8 plus 1. This one can be written now. Okay, let us write here. A square is equal to 8. 8. Now I will write m only. In place of this, I have written m, then plus 1. Plus 1. Now you have understood this 9 is written. Why 8 plus 1? Because there is plus 1. So plus 1 is required. So to get plus 1, 9, we have to write 8 plus 1. So let us take this one is m. So where? This you have to write. Where m is equal to 2q square plus 3q plus 1 belongs to z. So we have proved. By putting the value of r odd, we have done odd only. Because odd there is r equals to 1, we have got a square equals to 8m plus 1. By putting the value of r 3, we also have got a square equals to 8m plus 1. I hope you understand. Example number 3. For any integer, example number 3, yes. For any integer a is greater than equal to 1, show that a into a square plus 2 by 3 is always an integer. What is the condition given? A is greater than equal to 1. What we have to prove? A into a square plus 2 by 3 is also integer. So a equals to bq plus r 0. This one you have to write always. Now also we will take 2 integers. Let a and b be 2 integers. 2 integers. A is a and assume b equals to 3. B equals to 3, I think, yes. Why b is taken 3? Because there is 3, so that you can get something cancelled. So 3 is divisible by 3, so b equals 3 taken. Previous one 4 taken. We have got, I have already explained you. Now we will see b equals to 3. So what we will write? This one we will write again. A is equal to 3q plus r 0 r 3. Now what is r now? R is equal to 0, 1, 2. Because less than 3. So for r is equal to 0, a is equal to 3q plus 0. So a is equal to 3q. Is it not? A equals to 3 q. Okay. Then r equals to 1. Then a is equal to 3q plus 1. I went shortly because it is in the book only. Page number 110. You can see that. So r is equal to 2. So a is equal to 3q plus 2. What we have got? A equals to 3q. We have got a equals to 3q plus 1. We have got a equals to 3q plus 2. Okay. Now we will put the value there in the main part. What to show? This is also integer. We have got the value of a 3 times. Once 3q, once 3q plus 1, once 3q plus 2. 3 times we have to do this calculation by putting the value of a 3 times. Let us put now for a equals to 3q. A into a square plus 2 by 3. This is the term we have to show that this is also an integer. And by the time we have got the value of a, that is 3q. A 3q. So we will write 3q by 3q square means 9q square. I have written directly 2 by 3. 3 cancel. 3 cancel. We can write 9q cube plus 2q. In the both the term q is present. As I have told you every time, for every sum q is an integer. Q is always an integer. So 9q cube plus 2q. Q is present in first term, q is present in second term. So belongs to z. It is an integer. Which is an integer? While putting a equals to 3q, also we have got the whatever result, that is z. That is integer. So this is integer. So now we will put the value of a equals to 3q plus 1 in this. A square plus 2 by 3. Now what we will put? 3q plus 1. A equals to 3q plus 1. In place of a, 3q plus 1. A square 3q plus 1 whole square plus 2. 3. Let us do the calculation now. There is nothing to worry. Just whatever given, we will put the value only. You don't have to think much. 3q plus 1. Now directly I am going to do 3q whole square. 9q square plus 2 3 is 6q plus 1 plus 2 divided by 3. 3q plus 1 into 9q square plus 6q plus 3. Now 9, 6, 3. 3 can be taken common. 3 I am taking common from here. So multiplication, so you can add anywhere. 3, 3 is 9, 3, 2 is 6, 3, 1 is 3. So 3 cancel. So everywhere 3, this one you can, even if you don't multiply, actually no problem. Yes, no need to multiply. 3q plus 1 into 3q square plus 2q plus 1 belongs to z. Why? Because everywhere q is present. Everywhere q is present and some numbers are present. No x, no y, no nothing. If any other alphabets are there, then we cannot write belongs to z. Everywhere q is only there. As we know, q is always integer. So now a equals to 3q plus 2. A equals to 3q plus 2. One more calculation is left. 3q plus 2. What is there? A into a square plus 2 by 3. A into a square plus 2 by 3. Now we will put the value of a, that is 3q plus 2. 3q plus 2. 3q plus 2 whole square plus 2. This is 3. Let us do the calculation. There is nothing only to do the calculation, but calculation must be done in a correct way. If there is one silly mistake, everything will be wrong. Okay, 3q whole square is 9q square, twice ab, 2 into 3, 6, 6 into 2, 12, 12q plus 4 plus 4 plus 2 is there, 3q plus 2, 9q square, 12q plus 6. Now we can take 3 common here also. 3q plus 2, 3 taken common from here. What? 3q square, 3 4 are 12, 3 2 are 6. So whatever we have got, there is only q, nothing else. Q and number belongs to Z. So always remember that whatever result you get, you must get Q. You must get Q. Excluding Q, if you get any other alphabets, that will be wrong, because Q is only integer here. Example 4. Show that the square of an even integer is even and the square of odd integer is odd. Show that the square of an even integer is even and the square of an odd integer is odd. So we will take directly a equals to 2q and we will take a equals to 2q plus 1. Why? We will go to page number 108. There was written two definition, definition 1 and definition 2. That means idea of even and odd integer already I explained here today in this video only, that while a equals to 2q, that will be even, and definition 2, a equals to 2q plus 1, that will be odd integer. Page number 108. You will see page number 108. Then you can recall what is there in the page number 108. So here for even integer, for even we know that a is equal to 2q, and for odd we know a is equal to 2q plus 1. Page number 108. Now we will do squaring, nothing else, because square of an even integer is even. So this is even. For even, this is the condition. We will do squaring. Let us see even or not. Squaring both sides. A square is equal to 2q whole square. A square is equal to 4q square. A square is equal to 2 into 2q square. 2 into 2q square is 4q square. A square is equal to 2m. 2m, where m is equal to 2q square belongs to Z, because q is there. Very simple. This one also we will do squaring both sides. From where we have got this one? Page number 108. You can go back to page number 108. You can see today's video also. First video, first page, it is there. So a square is equal to 2q plus 1 whole square. Squaring, why we are doing? Squaring we are doing because in the question given square. Even squaring is done. Now we are going to do odd squaring. Squaring both sides. A square, 4q square, 4q plus 1. A plus b whole square formula I have done directly. You are in class 10 now, so you don't have to do again a square plus 2ab like that. Those who have problem to do directly, please do by putting the value correctly. Now, from here we can take 2 common. Why 2 common? Because we are not going to take 4 common. Because in page number 108, a equals to 2q given, a equals to 2q plus 1, not 4q plus 1. According to definition, we are going to do this one. So 2q square plus 2q plus 1. Let us write here now. A a square is equal to 2. In place of this, I am going to write m plus 1 where m is equal to 2q square plus 2q belongs to z. Why? Because q. So therefore, square of an even integer is even and square of an odd integer is even. This is odd integer, we have got odd. We have plus 1 is there. Even integer, we have got even only. 2m, no plus 1. If it is plus 1, odd. If it is no plus 1, even. Example number 5. Show that no number in this sequence 11, 111 like this. 11, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 is a perfect square. Perfect square, not perfect square. Why not? No number in this sequence is a perfect square. That means they are not perfect square. We have to show that. This is actually can be done very easily. 11 is equal to 8 plus 3. This is there in the book. You can understand actually yourself. 8 plus 3 we can write 4 into 2 plus 3. 4 into 2 plus 3, yes, isn't it? Yes. Here is written, you see page number 111, solution. Clearly each number in the given sequence is odd. First of all, they are odd. Therefore, if there is any perfect square in the sequence, then it must be square of an odd integer, because square of an odd integer is always odd. Example number 4, just previous example we have done. And so, square of the odd integer 8 is also the square of an odd integer is expressible in the form of 8m plus 1. Square of odd, these are all odd numbers. Example 2, wait. Example 2, show that the square of an odd integer can be written as 8m plus 1. That means square of odd integer must be 8m plus 1. According to example number 2, 8m plus 1. Odd number, for odd number, square will be always 8m plus 1. So here you have got 4 into 2 plus 3. Means 4m plus 3. Not 8m plus 1. Let us go to 111. 111 written 108 plus 3. 108 plus 3. So here 4 into 4 to the 8. 4 7 the 28. So you have got 4m plus 3. So we are not getting 8m plus 1. We are not getting 8m plus 1. That is why they are not perfect square. That is what written here. Very simple sum. You can see that in other words, the given sequence does not contain any square number. No number in the sequence. So 108 plus 3. So 1111 also done. And by 4 actually multiplied everything. By 8 it is not divisible. So not dividing. Actually directly we can do. 8 1 is 8. 3. This one 8m plus 3. Then 111. 8 1 is 8. 3, 8 4, 8 3 is 24. 5. 8 into 13 plus 5. Okay, this one m. But this is not 1, no. 8m, not 1. This cannot be. To get odd number perfect square, we have to get 8m plus 1. So in any sum in exercise also, if you get for odd square, odd number square, we will have to use 8m plus 1. Remember that. So till then, so I hope I am able to explain the exercise to make you understand properly, because I have not seen anything written in comment box, in inbox. So I hope all of you have been understanding everything very well, or I don't know whether you were intentionally not given any comments. That is, I am not sure. So if you could have given some comments, then I could have understood that whatever I have been explaining, that is going to your brain and you have been learning something easily from me. So that is what actually I expect. Anyway, till then, have a good day.